Hello everyone, we are back today for our second physics video, and today we're going to be going over Kepler's laws. More specifically, we're going to talk about his first, second, and third, and we're going to derive his third law. So, yeah, we're going to do Kepler's third laws, but first, some announcements. First of all, thank you to everyone here. I believe we are at 31 subscribers, and I have like 180 views with only my first two videos, so very much appreciated. And so yeah, thank you for everyone here. I really appreciate it. And second, our video schedule. So I will be most likely uploading 1 to 2 videos, 1 to 2 like short videos every Saturday, every weekend. But these days I expect more greater than 1. X is greater than 1, so my number of videos is going to be greater than 1, but they might be getting a little shorter. Next, also new topics. So by the way, if you guys would like me to explain new topics or derive new formulas, just mention it in the comments, and I'll be happy to try getting to that as well. So yeah, I'm open to new topics, like of the other sciences, biology and chemistry, and other branches of math. And next, for goals for the future. So my goal, this might be very ambitious, but I want to get to 100 subs by the end of May. So end EO month. The end of month May, I want to get to 100 subs. If we can do that, then I'm still working it out. I'll have some surprise. I might upload like several videos, but if we can get to 100 subs by the end of May, then I might do like a live stream or something. We'll see. So now back to the math. Let's get into it. So, what is Kepler's first law? So Kepler's first law states that all planets travel in elliptical orbits. So how do you envision this? So imagine it like this. Let's say I have a central mass right here, cm, right? So all planets will travel in an ellipse around this central mass. So we can demonstrate this like this. So our Earth is probably like right here. So all planets travel in a central mass, and by the way, in case you don't know, why is that? It's because there's a gravitational attraction between these two objects, and when the planets were first formed, this had lots of kinetic energy that made it want to travel in a straight line. So when you combine this and this, you get an elliptical orbit. So this is what Newton theorized. However, the actual reason is very different. So the actual reason is not because of any of Newton's laws. It's actually because of Einstein's theory of general and special relativity. So, although it's impossible to draw a 4D surface, imagine that this is the fabric of space-time. We live in a 4-dimensional world, 3 dimensions of space, and 1 dimension of time, which we cannot see, right? So what happens is that anytime something is in space, like a star for example, it bends the fabric of space-time, creating a gravitational wave, right? And we also bend the fabric of space-time, but not nearly as much as these huge masses of helium and of hydrogen and helium. So what's actually happening is that the fabric of space-time is being bent by these stars, right? So instead of it being a straight line, they're kind of like bending down in correspondence to the star. So as a result, the planets are rotating around it like in a bubblegum machine. So they're going in a spiral. And a lot of people have asked, so will they eventually go in here? Yes. The fact is that eventually the planet will go down the spiral and be consumed by the star. But by this time, like as with our solar system, by this time, our sun would have gotten so big, it would have become a red giant. It would have consumed everything here, and then would have either exploded or would have collapsed into a white dwarf. Pretty interesting to think about, isn't it? So yeah, that's Kepler's first law. Now, his second law. So Kepler understood that planets travel in ellipse. So this is based on the first one. So he said, if planets have to travel in an ellipse like he figured out, then they sweep out equal areas of distance in equal times. So how do you picture this? Well, usually we picture this with this famous kind of graph you might have seen before. It looks like this and like this. But then when the planet is on this side of the orbit, it's only like this. So what exactly does this mean? So what does it mean if planets sweep out equal areas at equal times? It means that this blue sector will always have a constant area. So how do we visualize that? It means that at one point, at one side is traveling faster, and on one side is traveling slower. So let's look at what these 2 points are called. So this point right here is the aphelion. So Helios means the sun. So the aphelion is when it's farthest away from the sun, when the planet is farthest away from the sun, right? And this point over here is the perihelion. It's when it's closest to the sun. So due to the fact that, if you look, this line is a lot longer than this line. So this like if our planet is on this side, it will not trace out nearly as much area as this one would. So it has to travel faster. It's as easy as that. On one side, the planet will travel faster than on the other side. So therefore, this is always constant. And now remember, the green is perihelion, red is aphelion. Now moving on to the most complicated law, Kepler's third law. So first, in order to understand this, we must look at an ellipse. We have our ellipse here, and in an ellipse, we have two axes. The major is the longer one, minor is the smaller one, this is the semi-major axis. It's half of the major axis, and this is the semi-minor axis, right? So Kepler's third law states that the orbital period squared is directly proportional to the semi-major axis cubed. And by the way, the orbital period is the time it takes for one complete rotation, right? So Newton actually derived this and turned it and without even looking at this formula, right? Without even looking at it, he actually derived it and turned it into another formula, which is much more used. T squared is equivalent to 4 pi squared over g times the mass of the central object, and all of this is multiplied by semi-major axis cubed. By the way, t squared is the orbital period, pi and g is the gravitational constant, pi is pi, obviously. So yeah, everything that I've not already defined is a constant, right? So now we are going to derive this. Let's get into it. So the first step that Newton did was he assumed a perfectly circular orbit. Now you might think, wait, this is contradictory. The first law says that all planets travel in an ellipse. So yes, they do. But he assumed this to make the calculations easier at first until he could transcribe it. So he said we have a perfect circular orbit, right? Perfectly circular, right? I mean this image clearly is not, but ignore that. So it's perfectly circular. We have the mass of the CO here, and we have our little blue planet here. So he said that, you know how gravitational attraction here, force here, they travel in this direction. So the first thing he did was he used his own formula. Force equals mass into the acceleration of the central body. And by the way, I labeled this as C, not CO, because when we're talking about this, we're talking about the F equals ma, where a is the centripetal acceleration. By the way, if you don't know what it is, you probably should if you want to understand this. But in basic terms, centripetal acceleration is the rotating acceleration. Just like we have acceleration and force, we have centripetal acceleration and torque. like we have velocity in regular objects moving in straight lines, we have angular velocity, right? So it like rotations have their own system of equations, so make sure you understand that before continuing this video. So F equals ma, and a is centripetal. So sorry about that. It's not central orbiter. So now moving on, he also used his next equation, the law of gravitational attraction. So it's the F equals big M, small m, or it's G times big M, small m, over R squared, and he labeled it like this. Yeah, so by the way, big M is the mass of producing object. I don't want to write MCO each time. So yeah, so what he did was, he did a really smart move. He set these equal to each other. G, M, M, R squared equals M. And then remember, if you remember from our kinematic equations, centripetal acceleration is equivalent to omega, which is angular velocity, squared times r. And by the way, I meant for this to be small m, okay? First thing is, these two cancel out, given, right? And then moving on. Then moving on, we have this. And then what he did was, he multiplied both sides by 1 over r, or divided both sides by r, same thing. So this cancels out, and then we have this. We have G M over r equals omega squared. Or sorry, Gm over r cubed. Sorry about that, because you multiply both sides by r, right? So big M, always remember this one, over r cubed equals omega squared. Perfect. But now we can also apply this, right? But omega squared, or actually in this case omega, is equivalent to 2 pi f, right? 2 pi, because it goes all the way around one time. Unit circle is 2 pi, if you don't know, in radians. So this is equivalent, because it goes around, and we have the f here, it's equivalent to 2 pi over t, which is the orbital period, obviously, right? Because it goes around one time, so the frequency is inversely proportional to the period, as you might know from waves. So now with this value of omega, we can simplify it in, and we get Gm over r cubed equals, what's 2 pi squared? 4 pi squared. Sorry, 2 pi whole squared equals 4 pi squared. So it's 4 pi squared over what's t squared? It's t squared. So now, getting to a little familiar, right? So we're going to apply cross multiplication, and we get t squared times Gm equals 4 pi over, equals 4 pi times r squared times r cubed. Okay, here, let me do this part. It equals 4 pi squared times r cubed, right? And then dividing, we get t squared. We can write it as 4 pi squared over Gm times r cubed. This is extremely familiar, except we're getting that payback now, right? We assumed it was an ellipse. We assumed it was a circle, even though it's an ellipse, and now we have r squared instead of r cubed instead of a cubed. So this is where, because we have made a big jump, now we have to deal with that. So Newton eventually did show, and so Newton was commissioned to do this because Robert Hooke and Edward Halley were tried to do this, and they got here and they found the same problem. So they commissioned Newton to do it, and the way he did it was, he saw an ellipse right here, and what he did was he solved for the time area ratio, right? And because this goes it goes slower here and faster here, he knew that even though it's an ellipse, this would eventually balance out. So yeah, this is not a trivial problem, right? Edward Halley and Robert Hooke couldn't do it. They commissioned Newton to do it, and it was eventually proven. So that's our equation. So this is not that hard to remember. If you don't remember it, you can just derive it. Gravitational. The hardest part here is gravitational acceleration and centripetal force. The moment you combine these two, they're your best friends, and you get the equation. So yeah, we can put little QED here, and there you go. We've derived Newton's third law. T squared equals 4 pi squared over g of the mass producing the gravitational force times a cubed. And by the way, I forgot to mention this, but some people might be wondering, well, if this system is kind of wrong according to Einstein with this theory of relativity and the 4D spacetime, why do we still use it? Well, even though the 4D spacetime is technically correct, these equations are very good approximations of what's going on. Like the kinematic equations, everything in classical physics is a very good approximation of relativity, because using the actual relativity formulas takes a lot more time. So it's simply easier for scientists and mathematicians to use these instead. So that's why it's a really good approximation, and it's almost completely accurate. So yeah, those are Kepler's three laws, along with a derivation of his third one.